What do you say, guys? Should we start? I think so, and people can enter as we take the introduction. So, most welcome all of you to this webinar on the topic revealing the effect of hidden damage in aluminum castings. And this is the third part of the topic manage the damage. And I will just show you, make some short introduction. So as I said before, we are 70 participants from 17 nationalities. And that's really nice. You are most welcome. It's a really international crew we have here. I will be the moderator today. My name is Madeleine. I'm part of the Weblon management team. We will start introducing the format, and then we will go over to the presentations, and you will meet the presenters very soon. After the presentations, there will be room for panel discussion, and after that, we will wrap up. If you haven't been on this webinars before, we have started as a project. It was very successful, a lot of participants during the 2 first years, and now we are continuing having webinars whenever we have something interesting to present to this community. And the rules, as usual, please have your microphone turned off during the meeting. You are more than welcome to put questions in the chat, and we are engaging you in the discussion after the webinar to share your ideas and questions. A recording will be available after, and but the discussions will not be recorded. Probably you know this, how to unmute your microphone, how to start your video if you want to do that, and also the chat function you have here. Now to the most important in the webinar, it's the presenters, of course, Professor Murat and Dr. Tony and Associate Professor Jacob. So I will hand over to you, Murat, please. The floor is yours. And I will stop sharing.
Thank you so much, Madeleine. Good morning, everyone. I am Murat Tiryakioğlu, Professor of Engineering from Jacksonville University. I will be joined by 2 colleagues from Jönköping University. Today, I'm visiting Jönköping University for a week, and I would like to take this opportunity to thank my colleagues who always make me feel welcome at this wonderful institution, especially Anders Jarfors, Tony Bogdanov, and Jakob Olofsson. Today, we're presenting part 3 of our Manage the Damage seminars. We started this in 2021. We gave the second in 2022. So after a 2-year absence, here is part 3. There will be some overlap between this one and the ones we gave previously, but I will go over this recap and what the damage is and where it comes from. We're going to talk about visible and hidden damage. There'll be 2 case studies in which we're going to show you results from our latest experiments. We'll talk about fatigue properties of aluminum castings. There will be a 3rd case study. And then we're going to talk about quantifying the damage, and that will be the 4th case study. And then we're going to finally wrap up with conclusions. Quality assurance of castings traditionally have relied on detection of pores. And the size and location of pores are usually specified in quality assurance specifications for example, an X-ray, so that the inspectors can make accept-reject decisions. This is especially true in aerospace. And the thinking is, if there are no pores, there are no problems with the casting. Casting is good, it's sound. There are no visible defects, and that's correct. But the results, unfortunately, this has created a mindset, even an obsession with pores that has taken us to adopt some technologies with, in my opinion, very low return on investment. And I see that in the recent trend in the acquisition of expensive micro CT scanners. There was a time when we looked into hot isostatic pressing, and that has not paid off well. And there's also, in my opinion, a wrong turn that has been taken by industry in this highly turbulent degassing and cleaning. There's a question mark right next to cleaning technique that I see in the foundries that I visit. And we're going to all focus on the damage in casting. So we're not talking about now quality, but the opposite of the quality, but where the damage comes from. I took this picture where I live on Jacksonville Beach in one of my daily walks. It's a beautiful beach. You should come and visit if you haven't done so. So what we see here is a substance that we are all familiar with. We interact with this substance, water, many, many times during the day. We drink it, we wash our hands, we wash our face, we take a shower, we cook with it. So in the end, we know how to deal with water. And one thing that's important to remember about water is that the surface of water is covered with water. Now, surface of liquid aluminum, on the other hand, is not covered by liquid aluminum. It's covered by a solid ceramic. And as long as this solid ceramic remains on the surface, it's harmless. But because we disrupt the surface so many times, that surface ceramic is incorporated or entrained into the bulk of the liquid, creating a non-bonded surface that we call a bifilm, because there are two films on each side. And that is the start of the damage. So the more we interrupt the surface, the more damage is given to the liquid metal. So the entrainment defect that we see is a folded over surface film due to the interruption or disruption of the surface. We also see air bubbles leaving oxide trails. We treat liquid aluminum as if it were water, as we're going to see in a few slides. So that is the root cause of the damage that come back to haunt us eventually in our aluminum castings performance. So when we don't like the temperature of our water, what we do is we put ice in it. There's no problem with it because the surface of ice is still covered with water. But if we put ingots in liquid aluminum, we again create damage. And the surface of the ingot is also covered by a thick alpha oxide. So we keep on giving the damage to the liquid aluminum as we disrupt the surface. And that all comes from the fact that we treat liquid aluminum as if it were water. So the result is bifilms in aluminum castings. And as you can see, several examples from the literature. It can be quite, it can be a huge bifilm like this, and you can see one half of the film on this shiny surface, and the other half was removed during grinding and polishing. Here's an extensive bifilm, and if you zoom in, you can see that this is an unbonded surface. It's basically a crack that is in our casting. So what is the current technology? This is a YouTube video that I found online, and I'm going to show you a small snippet of it. So we have a central furnace. And when the metal is ready, that metal has to be transported from the central furnace to the other furnace where the castings are produced. For that, we need a ladle, transport ladle, and that's taken away by this forklift. So there has been one melt transfer, and now it's brought to the holding furnace, and it's dropped from a height of, looks like several meters. And please notice the area, the top of the liquid metal. As you see, it's quite turbulent, and a lot of air has been entrained, a lot of surface covered by an oxide, and a lot of air has been entrained. So this is a perfect way to damage melts. And this all comes from our design of the production system. If we have a central furnace that requires not one, but two melt transfers, so every time we do a melt transfer, we seriously damage our metal. So what we saw here in this video, we use buckets. We use buckets in our aluminum production system. We love it so much that we pour from one bucket to the other. And again, in our mind, there's nothing wrong with it. It's liquid. It's just like water, but it's not water. And that mindset has to change. We saw how this melt transfer, when it went in, there was a turbulent reaction in the ladle, in the crucible, below in the holding furnace. And that's called a plunging jet. When you drop a jet from a height, it goes into another liquid. It's known as a plunging jet. It's a great way to entrain air into the liquid. It's well known as a fantastic technique to create a liquid and air mixture. Well, we don't want air in our aluminum castings and liquid aluminum, because that air is going to leave a trail, and in this case, it's going to be a bubble trail. And I'm going to show you a picture of that. But when we have this melt transfer, you can see that in the beginning, there's 65% air in where the liquid is supposed to be, and that gradually decreases, but we are giving serious damage to the liquid aluminum in these melt transfers. And the bubbles and the air that's entrained has buoyancy. It needs to go up. And you can see here a bubble that tries to go to the surface, leaving behind a trail, an oxide trail. That's going to act as a crack when it's under stress or tension. And you can see the bubble here that has had to stop because of the impinging solidification in front of it. It could never go to the surface. So the second technology we have, and sometimes this is required by the customers, and which is mind-boggling to me, is this cleaning process. And if I put some question marks, and let's watch this video. This is wildly turbulent cleaning, and some flux is put on the surface. The surface oxide is entrained into the bulk of the liquid along with this flux. And the results are usually okay. I think this is enough. It's an excellent way to hide the pores. and it's been designed to hide the pores. We don't, at this point, we don't know the exact mechanism of how it hides the pores, but it does. But one thing that we have found out is that it damages the melt further, and we found that it gives much lower elongation, which we reported in our recent paper that you can read if you want to, because we follow the damage in 2 foundries and found that it's consistent after this operation. Yes, the pores are eliminated, but the metal is much less ductile. So another technique that we use is the reduced pressure test. And if we were to have maybe a thought experiment, plot hydrogen content versus the density of the sample, our thinking is that if it's highly damaged, there is going to be a strong correlation between the hydrogen content and the density of the RPT specimen. And with decreasing damage, that correlation will be less strong. And when there's no damage, regardless of the hydrogen content, there would be no pores in our RPT samples. And this is clearly visible in the results by Dushpanar and Campbell. And you can see that we can clearly identify the trends for high damage and no damage from these experimental results. So what we're doing with degassing is we're reducing the hydrogen content, but we're making the damage invisible, or we're hiding the damage. And if hydrogen content is high, we can see the damage in our RPT specimens. And if we have high damage, we see a lot of pores. If we have low damage or no damage, we don't see any pores, which is a good thing. We can tell whether we have damaged melt or not. But by reducing the hydrogen content, we're basically shutting off that information. So what that does is we're basically using degassing to hide the damage. We're sweeping the dirt under the rug. And if it's under the rug, it doesn't exist. If I don't see it, it's not there. Unfortunately, life is not that simple, because they come back and present themselves when they're in when the casting is under performance, under stress. So this occurred to us some time ago, and I want to give you an example of the origin of our thinking. We were measuring the entrainment damage, both surface and air. We started with a very good metal, continues to cast A356 with very low pre-existing damage. We measured that. And we were looking at our RPT specimen. And of course, the first thing that you see is this large pore. That's good, because we were looking for pores. But then this curious feature that you may see here attracted my attention, and I asked, well, what is that? And when we turned the X-ray mapping on, you can see that this is for oxygen. This is clearly a folded oxide hiding between the dendrites near the pore. And then we started looking for these hidden bifilms. And we went to another location on the same micrograph. Like this, it looked curious. Okay, turn the X-ray map, and they are everywhere. And as you can see, there's some here, there's some there, there's another one here, there's another one there. So all these bifilms hiding right in front of us. There's a huge pore, but the pore did not expose all the bifilms. So it's clear that the overall damage is more extensive than what we can see with the pores. And that started our thinking. Well, okay, if that's the case, if we get rid of the pores, do we get rid of the damage? And obviously the answer is no. So we quickly realized that we're talking about the tip of the iceberg. The pores are only the tip, and the total damage is more extensive than can be measured from RPT or any kind of quality assurance tests. And in fact, quality assurance practices that rely only on the detection of pores clearly ignores the majority of the damage. So from then on, I started looking in the literature. Then we started looking at some experimental results that we're going to show. But there is always an oxide next to a pore. And in fact, calculations show us that it's impossible to nucleate a pore, either homogeneously or heterogeneously in liquid aluminum. So the only mechanism available for a pore to form is a pre-existing surface. And that pre-existing surface is the biofilm. So anytime we have a pore, there is a biofilm right next to it that remains unopened. And here you see something I found from the fatigue literature. It's referred to as fissure, but it's a biofilm. And now just looking at the pores as initial defect distribution in fatigue, which a mistake I have done myself, is misguided. We can now understand why cracks were observed to start propagating from pores on the first cycle in fatigue tests, because there's a crack right next to it, pre-existing crack. So how can we see this overall damage? The only thing that damage cannot hide from is a tensile stress. So here's an in situ test from the literature again. Here's a pore, and at the lowest, when tensile stress is applied, all these cracks start to form around the pore. And they are not really forming, they are just opening up. And these are the biofilms that were there to begin with. And from the same paper, you can clearly see, okay, there's something there, the crack, and that crack is a biofilm. It's associated with intermetallics and a pore. And when you apply a tensile stress, there's no resistance to tensile stress. It presents itself. It becomes visible. So the important concepts about damage are: pores are only the visible part of the overall damage. The real damage is much, much more extensive. Closing the pores, we demonstrated that it's a very low return on investment. And there are several examples on the first seminar. And I think you have access to those videos if you choose to watch them. Hydrogen is not a contaminant. Hydrogen cannot form if the pores cannot form pores if there is no pre-existing damage. All hydrogen does is to make the damage visible. So degassing hides the damage, sweeping the dirt under the rug. And the only thing that the hidden damage cannot hide from is a tensile stress or strain. This brings us to case study number 1. Jakob?
Yep. So then we will take a look at this case study where we are taking a look at this hidden damage in an aluminium alloy. So what we will be looking at is a high pressure die cast material where we have now done X-ray to confirm that there is no visible pores in this material. So if you go to the next slide here and start moving forward there, we can see the shape of the specimen. It's a high pressure die cast aluminium alloy specimen, as I said. You see the shape is not as we usually use in tensile testing. It's not a pure dog bone specimen. Instead, these are samples that were actually originally intended for bending fatigue testing. But we had an idea to test this in tension because we were looking at using a technique called virtual fields method to develop a constitutive model that describes the elastoplastic behavior of this material in capturing a larger variation of stresses than just purely tension load. But we tested this. If you test this in tension, you will create an uneven strain field. And as we said, there is no visible damage in these samples. So all damage that we see is then, as Turas introduced here, hidden damage. So you can see the strain field in the picture here. That's what we would expect to see in a tensile sample when we apply a tensile load to this sample. So what we did is then that we use digital image correlation. We put 2 cameras to observe a pattern that we paint on these samples, so we can in situ observe the strain distribution and how it proceeds when we increase the load. And as I said, the stress level is not the same throughout this. So we have an uneven loading here of the material, which also creates an unequal opportunity for defects. So as we will see here in the slides, there will be a competition between multiple sites. And the results here we can look at in different cases. So the first case here is what we call an early winner. So if you look at the strain field here, as we can see at a low load level, well, it kind of resembles what we saw in the FEM simulation, that we have a higher strain near the thinnest area here, but also a bit up there to the left, you can see that there's already something happening there, which is not really following the symmetrical strain distribution that we would assume here. So increasing the load, we can see that this spot actually clearly becomes the winner. It's really, the strain really increases much faster here than in the rest of the samples. And if we proceed to pulling it all the way to fracture, we can see that this is actually the point where the fracture is taking place. So we had a winner here in the race between the defects that was clearly rushing away from the start. It was a clear early winner here. When we look at the fracture surface of this sample, we see that there is a big oxide that just caused this strain concentration. And if we increase the magnitude, we can see that it is clearly a young biofilm here, which is draped over the microstructure, the dendrites, which are below here of the material. So comparing the strain fields that we see to the left compared to what we would expect to see to the right, we can see that that's definitely not behaving the same way as we would expect. So this hidden damage has really caused the material, the deformation and the fracture of the material to behave differently than it would if this would be just a continuous material. And we would just have dislocations moving, etc. The deformation behavior has really changed by this hidden damage. One good thing with using this digital image correlation technique is that we can also then go in and place local extensometers after the test on different positions. So if we measure the straining behavior of the strain concentration and at a symmetry point, which is located on the same level, but on the symmetry of the cross of the center line, we can see on the stress or the force strain curve here that we plot that the hidden damage here, the oxide here, has really caused a different straining behavior than the rest of the material, and it's much higher strain here caused by this, which also leads to the premature fracture here. The second group or case that we see is where we can see that the hidden damage is really fighting and competing all the way to the end. So here we see at the low load, we can see that, well, it's not as nice as you will see from the FEM simulation. It's something going on in the center here. There is 2 areas here that are really competing with the geometrical effect that we have. And also a bit higher up there, you can see that there's a clear red spot, which is also causing a high strain locally in the material. We can see that as the fracture proceeds through this thinnest area, but it follows, as we see, these red indications that were seen also in the strain field at this low load. And so this is really clearly the winner, and we had something in the top here that comes up in the second place in the run here on where to cause the fracture. Investigating this fracture surface closer in the SEM, we also see here that there's a very small pore, but also with an associated oxide, which has called, and also where you see this kind of dimple that goes down in the fracture cross section, we see that there are 2 oxides competing, that has caused this branching of the crack during the fracture. If we want to take a look at the second place position, we could see already in the paint on the DSE samples that there was a crack forming, but when we remove the paint, you can see in the SEM picture here that there's a big crack, and we can then use focused ion beam technology to make a small cutout from the front tip of this crack. So you see we're taking a very small sample. It's you see the scale down there, it's 10 micrometers. So it's a very small sample that we then can lift up and do a STEM EDS map of the chemical composition to see what it's that we have here. And looking at the map of the oxygen content here, we can see that this is clearly an oxide that has been also causing this crack that ends up now in the second place. So it didn't cause the fracture, but still it caused crack. And there was a competition going on between this crack, which is actually much higher up on the sample. So it's not subjected to the same load as the central area, but still it has been cracking here, the material. So we said that these were samples that were also X-rayed, where we could confirm that there was no visible porosity in the samples. But at the same time as we produced those samples, we also played around with the settings so that we also got some samples where we had forced pores within the samples. So we're going to take a look at them also. This is work that we are just publishing also together with Murat here. And the difference now between what we saw before is that we now also have the pores. So we also have, on top of the hidden damage, we also have the visible damage. And as you remember from previous here, these pores cannot have formed without these biofilms. And the effect that they cause is the kind of additional stress concentration that you get to add on top of what you already have due to the hidden damage. So you kind of inflate the problem here. So in a competition, we will see here that pores will have an advantage over the hidden biofilms, which are smaller and less inflated compared to the pores, which have now inflated the biofilms. So again, we have a case 1 here, which we call an early winner. You can see from this X-ray sample here that we have several pores within this sample. So when we take a look at the strain field during the load here, at a certain load, you can see that there is a clear strain concentration, which is also associated with the left porosity area. The porosity area in the central part is also, it's subjected to a higher load, so but it doesn't turn out fully as clear as the other one on top. And if we then combine these images and overlay the X-ray image on the strain field, we can see that there's something interesting going on here, because the porosity that we saw here, it's not connected to the surface, but we would expect the strain concentration to go towards the surface. But it's actually going to the right of the porosity. And we can see also in the central area to the right that there are porosities on the upper hand that are also matching with the strain increase that we see in the strain field. And also when they have the thinnest cross-section area, there are some small pores associated there. So proceeding and pulling this to the fracture in the next slide. Here we can see what we can then see in the microstructure on the fracture surface. We can see that you see the pore, the visible porosity that has been visible to X-ray, but zooming into this, we can also see that there is more cracking, and in these cracks you will see that there is oxide in the bottom of this pore that has also caused this crack to propagate, and also what causes the strain concentration to go to the right instead of to the left, to the surface, as we would expect here. There are multiple points where we can see this, and you can see that on the top region here, when we zoom in, you see the oxide quite clearly. And as we increase the magnitude in the SEM, we can see that the oxide is really draping the microstructure, both the dendrites and the intermetallic phases that you see in the microstructure here. Also in the center, we see that there's kind of an oxide which is not it's also extending into the material perpendicular to the fracture propagation which has taken place. The next case, you can see again that there is a competition between different defects here. So you see in the X-ray picture that's on the right side there, you can see that there is a clear big porosity, but there are also other effects that are going on when we look at the strain field. We can see on the left side there's a bit of this geometrical thing that we would expect, but on the right there is clearly something else happening here. And as we increase the load there, we can see that seems to be the winner. That's in the central area here, that there's clearly something causing a high strain here. But when we proceed to the fracture, it does not happen where we see the highest strain, because it actually goes higher up. And there you can see we have this indication of porosity also from the X-ray, but this was now, as you can see on the SEM, or the SEM picture there to the right, that the pore was actually on the other side, but we are not looking. So we didn't see the high strain concentration on our side, but we could see the effect of it. But it didn't look as bad as the other ones that we saw on the front. So this was kind of an unexpected site where it happened, if we will judge from the strain field. So, but remember again, this is also at a lower load than the central area is being subjected to at the same time. So we also can see then in the second place, runner-up, this that didn't cause a failure but had a high strain concentration. We can see that there are cracks on the surface, and you see that already in the paint. And as we saw before, we know that then also means that we have oxides at this places. To the right there's a combination of the visible damage and that was seen in the X-ray, but also the extending hidden damage, which has clearly separated and caused these cracks to appear, but not been the winners in the race to the failure. Yeah, with that, I think I hand over to Murat again, or is it Tony's turn? It's Murat first, yeah, I think. Yeah.
It's my turn. Thank you, Jakob. Okay, so fatigue failure is, as we learn in metallurgy books or mechanical engineering books, we have been all taught that crack initiates somewhere. And then it can be from a design flaw, it can be from a defect, or it can be from some sort of a stress concentration. Then the crack becomes a long crack. And the long single crack propagates in solid, defect-free material. That has been the thinking. So one single crack propagates until the final fracture occurs at the critical crack length. That's what we've all been taught. With the emergence of new technology showing us in situ testing, all of this thinking is now being challenged. So I'm going to show you a few examples that we saw in the literature before turning it to Tony. These inactive oxides or the hidden damage during in situ fatigue testing. Here's an example of 319 alloy. We're looking at, we can see two pores here, one pore on the right-hand side, and there's another one here. And we're at the 10th fatigue cycle. And by the strain fields, you can see that there is a field between, and there's one thing that at least that opened up in almost at the midpoint between the two pores. And at the 30th cycle, you can see one crack here that already started propagating, but there are also multiple cracks that are opening up, and they started to propagate as well in the direction that's much advantageous for them to release the energy. And in the end, if you look at the strain field, not in the end, but at the 30th cycle, you can see a crack that has already started propagating from this pore. There's another one that is going inside. A third one that propagated here. There are many other cracks that have started propagating. And obviously, in the end, you can see that those cracks will all join together to form one large crack. So that's different from the crack propagation that we've been taught. These are all small cracks that opened up and that finally joined forces to form the long crack. So it's all small crack, not a big long crack that got initiated from a single point. There are multiple crack initiating sites. Obviously, these are bifilms. And that start immediately with almost no threshold. And that's obviously small crack propagation. And that the crack propagation follows the cracks that open up in front of the main crack. So small cracks join forces to become the main crack. And there are also large flat areas on the fracture surfaces without any beach marks that were reported, like this one. That's a clear indication of a bifilm. This brings us to case study number 3. Tony?
Yes, thank you so much. Now I will present a little bit of the work that we have been doing over the last years, trying to actually show how the hidden damage will be shown in the fatigue crack propagation. And to be able to do that, we have done a lot of experiment in the in situ cyclic testing that we have at Jönköping University, where we can produce small CT samples that we put inside our SCM. And from this, we can get a lot of information. So here we actually see what we see in the SCM. We look on a view 300 times 300 micron when we do the test. And we can get the data out in terms of the grain size using EBSD. And we can also apply so we can see when the crack is propagating during the test. And here we can see some interesting feature in front, and applying digital image correlation that Jakob was presenting before. We can actually see that we have a strain concentration where something is happening before. But one of the best advantages is that we actually can follow it live while the test is running. So here we can actually see the crack propagation forming during the test. And what we see is that we have crack propagation to the top left, but we also see that we have a secondary crack appearing in the center, and we have a lot more cracks in front of the propagating crack. So if we continue, we did this on different material. The first material we started with was a 42,100 alloy that we hit the material. And here we're starting to see this interesting behavior that we have actually a big crack in front of the propagating crack. It has not even started the crack propagation. But in an area like 200 microns away, we see this big crack opening up. And that if we continue, this crack will be the final failure in the end. So here we see that we have new crack initiation spots that actually will coalesce to others, and that will be the fatigue. And we confirmed that this was an oxide film in this crack propagation in this area by using EDS on the surface, in this case, in this paper that we worked with. I will show you a little bit further, more data about this, what we see. Here we see an A357 alloy that was also, if we move the starts, we can see the crack propagation. But here we start to see that we have a lot of cracks in front and in several different areas. The video is not going so good in my computer at least, but we also see that we have a crack in the end down there that is starting to go up. And according to what we learn is that the strain concentration should be highest at the notch, but we are here to see when we continue the video that the crack will coalesce and create the final failure. And we have shown that these are oxide films that are opening up at early stage of the propagation. And also in this sample, the sample were hit, so we didn't have any porosity visible. Continue to this one that we actually show that how many hidden damage do we actually have in the material when we look on this. We saw here between 900 and 1,000 cycles that we have a lot of small cracks opening up. And since we have our SCM and we have the focused ion beam, so we can actually investigate what is happening in front of the propagating crack. So we decided to dig into this further in this paper that we published. So if you take the next slide, we decided to take one area in front of the propagating crack and see how does the material look when the material is in front of the propagating area. You can take the next slide more. So we decided to interrupt the test that we see in figure number D here. Then we use the focused ion beam milling to actually take out the area in front, so we actually can create a 3-dimensional volume. And then using a software, then we can actually highlight all the cracks that we have in the material with red color and all the intermetallic in blue. So this is an area of 250 slides, so we can actually see what is happening. So if we go to the video in the next slide, what we see on the left side here is the propagating crack front. And when it starts to slice this one, it will now add all the cracks. And what we observed is that we have a lot of small secondary cracks everywhere in front. And they are not directly linked to the intermetallic phases in this case. So this is actually a clear evidence that we have a lot of small bifilms opening up like cracks that will assist the propagating crack front and coalesce with the previous crack. So we will have a lot of small cracks competing about the fatigue failure. Then I leave it to you again, Morat.
Thank you, Tony. So how do we quantify the damage? Obviously, based on our discussion, the X-rays are not the most helpful. CT scan will probably give you the same results. But we said that damage cannot hide from a tensile stress. So let's build on that. So, essentials of tensile deformation. It's always a competition between further deformation and final fracture. So at any point, at any stress-strain combination during deformation, the lowest energy option is taken. So if it takes lower energy for further deformation, the material is going to choose to deform, whereas if the energy is lower for final fracture, the fracture will take place. So ductility is a direct measure of the energy absorbed during deformation. So that brings us to the last point. Elongation, which is a great measure of the energy absorbed during a tensile test, is a measure of total damage. So taking that, some years ago, working with Professor Campbell and a colleague of mine from Greece, we looked into the aerospace and premium casting literature. So we put all the data we could find on a scatter plot with yield strength on the x-axis and elongation on the y-axis. And when we focus on the maximum numbers, you can see that there's a trend. So we call this the ductility potential. And for aluminum silicon castings, we can write this ductility potential as 36 minus 0.064 times yield strength, and this is in megapascal. So that will give you a percentage. So at any given yield strength value, you can calculate a ductility potential of that alloy. And this brings us to the structural quality index. Now that we have a metric that we can compare to, we can have a quality index, QT, whereas this is our data point that comes from our tensile test. It has a given, obviously, it has a yield strength and an elongation. And if I can then calculate a value from the previous equation, and similar equations exist for aluminum copper alloys if you are interested. And then I can define the quality index as the elongation that I obtained divided by the ductility potential. So what is the measure of damage then? Damage is the part that I'm not getting from my casting. And that's the loss due to damage. And our thinking is that there are 5 different distinct areas. If your quality index comes out to be 0.25 or 25% or less, your castings are highly damaged. Between 25% and 50%, you have moderate damage. 50 to 70%, you have low damage. And after 70%, they start to neck. So that's very uncommon in cast aluminum alloys, but that brings you to the very low damage. And the last area is where we don't have any data yet, but we hope that with improving quality of our melt, we will get more, this ductility potential will shift even further up. Having said that, that brings us to case study number 4. Jakob?
Yep. So this next case study that we just recently been working with and is just in the pipeline of publishing right now is an example where we're looking at the quantification of hidden damage in a high-pressure die-cast component. So now we're taking it from tensile bars into a component. So this is a work that we have been doing together with Magma GZI technology in Aachen, and just been, as I said, just about to publish these results, and it's been a collaboration here in this project. So what we're looking at is a high pressure die casting, as you can see schematically here on the picture. And in order to evaluate then the local material properties and see how it varies throughout the casting, we have done tensile testing on several different locations on different positions of this casting. You can see they are labeled here A, B, C, D, E, F, G. And for each location, we have been taking 20 specimens that we have been evaluating, doing tensile test of. They have been tested in tension. And the yield strength of this material is around 145 megapascals. So as Murat just mentioned, the ductility potential, that will be around 27% of this material, I think was the value. But then we wanted to see, is there a difference between the different locations? Are they actually behaving differently, or do we have, are the samples that we take, are the samples from the same distribution or from different distributions? Do properties change with location, as in this case? And the final results that comes out of this, we also compare to another location where we have visible porosity, because I forgot to mention maybe that in these 7 positions that we're looking at here, it has been confirmed that there is no pores. It's been CT scanning of these samples to make sure that there is no visible damage in these locations. So first, we're taking a look at how to compare the different positions. And that's the initial idea was that, okay, let's take samples, and then you do this, that you take a look at the average value of this. That's typically what we do when you do tensile tests. And you think that, okay, there's a slight change in the average values, and why can that be? And you try to explain that. But when you start talking about elongation, you have to really understand the physics behind this, is that this is a weakest link problem. So that will follow a distribution. It's not one specific value that you will end up with. So in order to compare instead, if these positions comes from different statistical distributions, we apply statistical test of the data sets from each position. And the idea with this test is to compare the average values in this case that we're looking at here. And it's called a Mann-Whitney test, where you compare the distributions and see if they can be expected to be from the same distribution, or is there a statistical significant effect that they are from different distributions. So what we're looking at in the table here is the p-value that comes out from this test. And if that is below 0.05, then the distributions are different. And interesting here is that the one point that sticks out when we apply this test, we do the combination. We test, for example, an A and B together, A and C together, A and D together, and you compare this, is that position D, clearly, as marked here with the red lines, comes out. It's different from the others. The other ones, when you compare them to each other, there's not a statistically significant difference between those locations. So the failure behavior of the different positions is actually the same in all positions, even though you do see, if you take a look at just numerical average values, it's the underlying distribution is still the same. But location D is different. And that kind of struggle was a bit of struggle to realize why is that? Because why does this place fail differently than the other ones? In the simulations we first looked at the solidification simulation, see if there's a difference in microstructure, but we didn't really see anything clearly. But when we went into the filling simulation and we took a look at the measure called air contact time, we could see that there is actually something interesting going on here in this region. As you can see, this is in the end of filling that we see how the melt fronts are approaching this location. And it's actually 3 different melt fronts coming from different regions. You can see one coming from above that has been in for a long time in contact with air. And if you proceed to the next image, you see that these 3 fronts has kind of smashed together and formed a turbulent area here where these oxides films that have now been generated during this long air contact time is being swirled into the melt here. And as the filling continues in the next slide, you see that the area here, also proceed to the next slide, where this is the last one, where we have this position D, has been subjected to quite a significantly higher air contact time. So the time that has been proceeding where the melt has been mixed with air and the possibility to create more oxides is actually much higher in this position D compared to position E, which is just next to it. Geometrically, they are very close. Also looking at the velocity that these positions has been subjected to, we'll see that position D has had a significantly higher filling, been subjected to higher velocity during the filling. So there's been a much more turbulent flow of this melt that comes up here. So that's could be a possible explanation for why D is different. Then we also took samples from these positions and again applied this digital image correlation. And the 2 samples that you see on your left side is now from position D, which is the location that stood out as different. While the 2 on the right is from the area which is actually the best, which was just next to the really bad position. So you have really good properties. And you're looking now at the strain field when all of the samples are subjected to the same level of deformation, corresponding to around 0.4% of total strain. So we're around the yield point of the material. And interesting is that the 2 samples to the left which are also now suspect to contain much more level of oxide, is showing a much more dispersed strain field. You can see that there are small histograms included in the scale bars, and you can see, especially for the sample D2, you can see that the strain distribution is actually very dispersed. It's big variability of the strain because we have this large amount of hidden damage, which is actually causing a lot of strain concentration. So there's a competition between all of these internal damages in that. In the samples to the right, sample E1 and E2, we can see that they are much more narrow. The histograms are much more narrow at a certain level of strain. And here the damage, hidden damage, the level of hidden damage is lower. So that really explains why this position D comes out as different. And if we proceed to the next slide, what we can do then is we know that, okay, the elongation values here are expected to follow a statistical distribution. And then we can fit the parameters of a Weibull distribution to these samples and plot these Weibull distributions. And that is what you see here. So the solid black curve is the distribution for all positions except the D1. So even if We have good samples, we have bad samples, they all come from the same distribution with an average of around 7-8% somewhere. But it's quite a wide distribution, and that's the general material quality or elongation level that we have in this material. The black dashed one is position D, and you can see that is clearly following a distribution which is different, and it has a much lower average value of around 4%. So it's clearly different. But let's also take a look at the samples that I mentioned that we have clear visible porosity. On top of this hidden damage, we also have the visible porosity. And that's the red curve. That's the X samples. So that's the samples with pores. Position D are samples without pores, but with a lot of hidden damage. And the general curve is the one with for all the other locations where we have. And you remember I said that the ductility potential of this material was around 27%. So that's the potential that we should be able to reach. But due to the fact that we have visible and hidden damage, you see we are cutting away and we're removing quite a lot of elongation. We are only reaching about 3.5-4%. If we focus on removing the pores, what do we get instead? Yeah, still we have, if we have the high level of hidden damage, it's not a really big gain that we get. But if we focus on lowering the hidden damage, we have a larger increase in elongation. We can see that there's a lot of fight to get onto the 27%, but focusing on reducing the hidden damage gives you more effects than removing just the porosity. So the visible damage, it does increase the effect of the hidden damage, but it doesn't remove the hidden damage. So battling only the pores, as we see it, is kind of misguided. So, Murat, I think I leave it to you to wrap up the conclusions here.
Yes, thank you, Jakob. So in conclusions, we can all appreciate that pores are only the visible part of the damage. The total damage is mostly hidden and much, much more extensive. I think we've clearly shown that. We made that case very strongly. Many biofilms hide in castings. They remain unopened and undetected during quality assurance checks, especially if you rely on X-rays or CT scans. You cannot see them. One thing they cannot hide from is a tensile stress. They open up during tensile tests and the fatigue testing. Upon tensile stress, there is a competition between multiple biofilms to cause the final fracture. All pores have biofilms around them, which also open up during in a tensile stress. What pores do is they act as stress concentrators, so the biofilms next to them have a larger chance of winning the competition to the final fracture. The fatigue of cast aluminum components is dominated by damage. The cracks initiate early from pores or hidden damage. The crack propagation that we were taught in school does not apply in this case. It's mainly linking of simultaneously growing cracks from biofilms. There is no long crack growth. It's all small cracks. So at this time, being a certified quality engineer, I can easily say that the quality assurance practices built on detecting only pores are outdated and misguided. Beveling pores should be the first step in quality improvement, but not the last step. It's just you've just taken the first step in climbing the mountain, but there's a whole big mountain left to climb. So you have to quantify the damage to manage the damage, and we've given you a tool that you can start using now from your tensile tests. And we all think that it's time to design and develop entire production systems that eliminate these melt transfers, that minimize or even eliminate damage. There's a whole lot that the aluminum metal is trying to give us that we've been managing to neglect. With that all said, thank you for attending. Tack så mycket. Teşekkürler.